Richard Feynman was 24 years old when he walked into a room full of the greatest minds in physics and proceeded to have his entire theory dismantled by Albert Einstein himself. And what happened next had nothing to do with being right. It had everything to do with something far more rare. Princeton, 1943. The war was swallowing the world whole. Somewhere in the desert, the Manhattan Project was quietly changing history. But inside a small seminar room on campus, a different kind of collision was happening, one not between atoms, but between generations, between the old god of physics and something new, raw and barely formed. The front row that afternoon read like a who's who of scientific legend. Einstein, 64, had already reshaped civilization twice over. Wolfgang Pauli sat beside him, a man so rigorous, so merciless in his evaluation of bad ideas that physicists had coined a phrase for theories he dismissed: not even wrong. John Wheeler was there too, electric with ideas, a man who would later give the world the term black hole. Surrounding them were Nobel laureates, theorists of the highest order, minds that had spent decades shaping the landscape of modern science. And at the front of the room, chalk in hand, heart hammering, stood Richard Feynman, a graduate student, unknown, 24 years old. His advisor Wheeler had put him up to this. Feynman had been developing something radical, a new way to think about quantum mechanics from the ground up, not a patch on the existing theory, a reinvention. Wheeler believed in it, but Wheeler was famously drawn to wild ideas. The real question was whether anyone else in that room would see what Wheeler saw. Feynman steadied himself and began. To understand what was at stake, you need to understand the problem physics had been wrestling with for nearly 2 decades. Quantum mechanics worked spectacularly well, in fact. It explained the structure of atoms, the behavior of electrons, the entire foundation of chemistry. Scientists had every reason to celebrate it. But the celebration had a crack running through it when physicists tried to merge quantum mechanics with Einstein's theory of special relativity, when they tried to describe particles moving near the speed of light using quantum rules. The mathematics went haywire. Calculations that should have produced clean, finite answers kept spitting out the same monstrous result: infinity. Not a very large number. Infinity. An answer so nonsensical it was effectively a confession that something somewhere was deeply broken. This was the crisis at the heart of quantum electrodynamics, the branch of physics describing how light and matter interact. Decades of brilliant people attacking the same problem, and the math kept collapsing under its own weight. Some physicists suspected the theory was beyond saving. Others kept patching, stitching, applying clever mathematical tricks to make the infinities temporarily disappear. Tricks that worked on paper but left an uneasy feeling that nobody truly understood what they were doing. Feynman and Wheeler had taken a completely different road. Instead of fixing the broken machinery, they asked whether the machine itself was the wrong design. What if you described particles not as objects traveling through space, but as travelers through all possible versions of space simultaneously? What if a single particle moving from point A to point B actually took every conceivable path at once, the straight line, the curved arc, the impossible loop, and the final outcome was the result of adding all of those possibilities together? This was the path integral formulation of quantum mechanics. It was strange, it was disorienting, it required thinking about particles moving backward through time, but it was also, in its own way, beautiful. And more importantly, it seemed to work. That was what Feynman was explaining to Einstein. The presentation built steadily. Feynman drew diagrams, traced arguments, showed how this approach could handle things that tripped up conventional methods. The room was listening carefully. This much was clear. Then Feynman reached the part that would define the afternoon. In standard quantum electrodynamics, the electron was thought to interact with its own electromagnetic field, a phenomenon called self-energy. The electron generates a field. That field carries energy. Therefore, the electron's total energy includes a contribution from its own field. Simple enough in concept. In practice, it was catastrophic. When you calculated this self-energy, it blew up to infinity because the electron's field extended outward without bound. Physicists had been fighting this infinity for years. Feynman and Wheeler's proposed solution was audacious: eliminate self-energy entirely. Build a theory where particles never interact with their own fields, only with each other. No self-interaction, no infinity, no problem. Feynman laid this out carefully. He showed the equations. He walked through the reasoning. He finished, looked up at the room and waited. Silence. Einstein raised his hand. He stood slowly. He thanked Feynman genuinely, not dismissively. And then, with the patience of someone who had spent 60 years thinking carefully about the structure of reality, he walked to the blackboard and began drawing. The objection was surgical. When a charged particle accelerates, Einstein pointed out, it radiates energy outward. That energy has to come from somewhere. In the standard picture, it comes from the electron's self-energy, the field the particle carries with it like a cloak of stored potential. Remove that self-energy entirely, as Feynman proposed, and you've eliminated the source. The electron still radiates. The energy still disappears into space, but now there's no way to account for it. This, Einstein explained quietly, appeared to violate conservation of energy, one of the most bedrock principles in all of physics, not a technicality, a cornerstone. Feynman searched the argument for a foothold. He couldn't find one. Not then. Pauli followed up, characteristically blunt. What about quantum fluctuations? What about the Lamb shift? A tiny but precisely measured energy discrepancy in hydrogen atoms that had recently been confirmed experimentally. The standard explanation relied entirely on the electron interacting with its own field. Remove that interaction and the effect simply vanishes, except it demonstrably doesn't vanish because experimenters had just measured it. The questions kept coming. Wheeler defended the framework gamely, arguing these were engineering problems inside a sound architecture. But the room's skepticism was palpable. The seminar ended. The giants filed out. Einstein passed Feynman near the door, offered a polite nod, and was gone. Feynman stood there feeling like the floor had been removed. He didn't sleep that night. He went back to the mathematics alone, filling pages in the dark, not with the wounded pride of someone trying to prove a critic wrong, but with the honest focus of someone who suspected the critic might be right. And slowly, over hours, it became clear. Einstein was right. The energy conservation problem was real. The theory in its current form was broken. But here's the thing about genuinely important ideas. They are rarely born complete. As Feynman dug deeper, he began to see that the flaw was not fatal. It was instructive. The mistake wasn't in the destination. It was in how aggressively they'd tried to reach it. You couldn't eliminate self-energy entirely. That was too blunt an instrument. But you could rethink how it was handled. You could be more precise, more careful about which infinities were physically meaningful and which were artifacts of a mathematical framework that hadn't caught up with the underlying reality. Over the weeks that followed, Feynman and Wheeler revised their approach. They preserved the core insight, the path integral, the sum over all possible histories, but refined how electromagnetic interactions were treated. And in that process of refinement, Feynman began developing a concept that would eventually transform physics entirely: renormalization. The recognition that certain infinities weren't errors to be eliminated, but signals pointing toward redefinitions of fundamental quantities like mass and charge. He hated it at first. It felt like sweeping dirt under a rug, but the answers it produced matched reality with a precision that bordered on the miraculous. Months passed. Feynman was walking through the Princeton campus, lost somewhere inside a calculation, when he nearly collided with Einstein in a hallway. They stopped, an awkward beat. Einstein spoke first. "Mr. Feynman, I've been thinking about your seminar." Feynman braced. But what Einstein said next wasn't criticism. It was something rarer. Einstein told him that he had been too harsh in the room that day, that what Feynman was attempting, not the specific mechanism but the ambition behind it, was genuinely uncommon. Most physicists, Einstein said, spent their careers decorating the same building. Feynman had been willing to burn it down and ask whether the location was wrong. He told Feynman about his own early years, before relativity, before fame, when the entire physics establishment was devoted to preserving the concept of absolute time and a luminiferous ether as the medium through which light traveled. Einstein had looked at that consensus and concluded it was wrong. Not incomplete, wrong. The ether didn't exist. Time wasn't absolute. space itself bent. He hadn't patched the old theory, he'd replaced it, and the response for years was confusion and resistance. If you are right, Einstein said, and your mathematics matches what nature actually does, they will come around. They always do. It just takes time. Then he asked Feynman a question. What if you're wrong? Feynman hesitated. Einstein answered for him, then you will have learned where the boundary is. That is not failure. That is the entire point. He walked away. The whole exchange lasted perhaps 3 minutes. What Einstein recognized in Feynman wasn't technical perfection. Feynman's theory had been wrong in specific ways. Einstein had demonstrated that clearly, and Feynman knew it. What Einstein recognized was something harder to teach and harder to find, a mind that refused to be satisfied by inherited answers. By the 1940s, Einstein had spent years working largely alone on his pursuit of a unified theory of physics, an attempt to weave gravity and electromagnetism into a single coherent framework. The mainstream had moved on. Quantum mechanics was the dominant language, and Einstein remained fundamentally skeptical of it, convinced that it was describing shadows on a cave wall rather than the actual structure of reality. This put him in an unusual position. He was revered universally and agreed with increasingly rarely. The isolation of working against the grain, of being decades into a project the world thought was a dead end, was something he understood viscerally. And when he looked at Feynman standing at that blackboard with a half-formed theory full of real problems and real ambition, he didn't see a student with wrong equations. He saw the same instinct that had driven him into that hallway in 1905 with a paper that would rewrite time itself. The instinct that whispers, the foundations might be wrong, start earlier. Ask the question nobody else is asking. That instinct, Einstein knew, was the most valuable thing in physics and the most fragile. Feynman would go on to win the Nobel Prize in Physics in 1965, 22 years after that seminar. The path integral formulation became one of the foundational frameworks of modern theoretical physics. Feynman diagrams, elegant visual shorthand for particle interactions, became the universal language of quantum field theory. Every graduate student learns them. Every paper in particle physics uses them. And quantum electrodynamics, the theory Feynman helped rebuild from the ruins of that presentation, became the most precisely verified theory in the history of science, predicting the magnetic behavior of the electron to 11 decimal places. To put that in perspective, it's like calculating the distance between two cities on different continents and being accurate to within the width of a single human hair. Einstein died in 1955, a decade before Feynman's Nobel. He didn't see the full arc of vindication, but he saw enough to know that the young man who had stood nervously at that blackboard in 1943, equations crumbling under criticism, had something that couldn't be taught and couldn't be faked. Here is what this story is actually about. It is not about genius. It is not about being right. It is about the rarest combination in any intellectual pursuit: the willingness to be publicly wrong, the honesty to acknowledge it immediately, and the stubbornness to keep going anyway. Einstein's criticism in that seminar room was not an attack. It was a stress test, and Feynman passed it not by defending his theory, but by going home and tearing it apart himself. That response, that reflexive honesty in the face of failure, was precisely what earned Einstein's respect. Not the equations, not the cleverness, the character. Science advances the way it does because of dialogues like this one. Not through isolated moments of brilliance, but through the collision of ideas, the pressure of criticism, the slow revision towards something true. Every Feynman diagram drawn today carries within it the ghost of that afternoon, Einstein at the blackboard, a young man listening hard, the silence of a room full of giants waiting to see what he would do next. He chose to learn. That's the whole story, and it's enough.